30, and today we will start discussion on laminar non-premixed flames or laminar diffusion flames. Diffusion, or we can call it non-premixed. We discussed laminar premixed flames and turbulent premixed flames. Now we are looking at laminar diffusion flames, laminar non-premixed flames. So you already know what non-premixed flames are because we discussed that at the beginning of the semester. And the most prominent example that we discussed those days was that of a candle flame, right? So this is a diffusion flame. And what do we call a diffusion flame? Where the fuel and the oxidizer are not mixed prior to combustion. So in this case, fuel comes from the wick and goes towards the flame. The flame is roughly here. The flame is, and the oxidizer is the air. So the oxygen of that oxidizer comes and meets the fuel. Now the fuel in case of a candle is a heavy hydrocarbon. So it's a C16, C18 or maybe C20, that sort of a hydrocarbon, and that molten wax rises up the wick, then it vaporizes, moves towards the flame, oxidizer comes from the other side, they meet, and then you get a flame. So this is a candle flame which we know of. And we understand that this will be different from a premixed flame. And in a premixed flame, actually, fuel and oxidizer are mixed. That helps in controlling pollution. And in a non-premixed flame, they are not mixed beforehand. So non-premixed flames will typically be more polluting, and there will be production of soot quite often in non-premixed flames. So non-premixed flames are more prone to producing soot, whereas in premixed flames you are less likely to get soot. So this is one difference. The other difference is premixed flames do have a very significant stability issue. We saw that flames can flash back, flames can lift off burners, and flame can also get blown off. Now it's not like non-premixed flames, that is diffusion flames, do not have stability issues at all, but the stability issues are typically less. So if you want more stable combustion, if you are not very sure about whether a premixed combustion of the fuel air mixture that you have will give you an anchored flame, if you are not very sure about that, then non-premixed flames is sometimes a better option. But non-premixed flames can produce maybe soot or maybe more pollutants. The reason premixed flames are less polluting and do not produce soot or produce less amount of soot is because the fuel and an oxidizer are mixed at the molecular level. So that helps in controlling pollution. That helps in actually getting fuel species or some derivative of the fuel species to get quickly consumed by oxygen, because a fuel molecule or a derivative of a fuel molecule gets oxygen around it. So that helps. Now what do I mean by a derivative of a fuel molecule? Remember the discussion that we had about candle flames. This fuel vapor moves towards the flame, and on its way it can actually break down because it's in the high temperature zone. So a heavy fuel molecule can break down to smaller fuel molecules, smaller chemical species, smaller hydrocarbons, and then move towards the oxidizer. So all this, whether the fuel molecule itself or some broken down version of it, will get more oxygen if fuel and oxidizer are mixed beforehand. So that can help. So these are some of the differences between premixed flames and non-premixed flames. Premixed flames more pollutant issues, non-premixed flames more pollutant issues, and premixed flames less pollutant issues, and on the other hand premixed flames have more stability issues sometimes. Now how do we study non-premixed flames? We are taking the same approach as before. We are taking the laminar version first, then we are going to the turbulent version, just as we did for the premixed flame. Now for premixed flame, we took an example of a simple one-dimensional flame and tried to analyze that and learn something about premixed flames from there. Where do we start for non-premixed flames? Of course, we'll start with laminar non-premixed flames, but do we start with something like a candle flame? that will be more difficult. We want to have a flame which is better defined, which is more under our control. Whereas a candle flame is more of a natural thing, because it is this wax which will melt because of the heat coming from the flame, and then the molten wax will rise up the wick and things like that. It will be easier if we just take a tube and send some fuel through it, and then the fuel is surrounded by, in any case, the oxidizer, which is air, and then just see what happens. That problem appears to be an easier problem to solve. Okay, so we always start with the easiest problem that we have. So what I meant is that you can have a tube like this and send fuel through this, and in any case you have air outside it, and you will get a flame, right? So this we will call a non-premixed flame, and this non-premixed flame will be laminar if the flow situation is laminar. Because if there are not too many fluctuations in this flow, if the velocities are not high, okay, if the stream which is coming here is not turbulent, or outside there is not a lot of turbulence, then you get a laminar non-premixed flame. So this is better defined than the candle flame. So this is the sort of flame that we like to study. Now, apart from the candle flame, do we know of other examples of non-premixed flames so far in our discussion from the beginning of the semester? Yeah, actually there is another flame, which is the Bunsen outer flame, okay, which is also non-premixed flame. So if you recollect, I did mention some time back that you get this conical flame, which is the premixed cone, because through this tube you are sending fuel and air, but outside you get a glow, and this part, the outside part, is in fact a non-premixed flame. So whatever is not burning in the premixed cone, let us say some carbon monoxide, some hydrogen, that is going out of the cone, and then it's meeting air from outside, and then it's burning and giving you a non-premixed flame. So this is a non-premixed flame. So we are familiar with this. We have seen this. Now, the cooking stoves, for example, a gas stove, that's not exactly premixed, but that actually not exactly non-premixed either. What is done is fuel and air are often mixed, and it's kind of partially premixed, and then the fuel air mixture comes out of the burner holes, and then outside there is air. So the secondary air completes the combustion. So a lot of burners in industry can be like this, that there is some amount of premixing which is done in the fuel, but then it also gets secondary air to complete combustion. So there is a non-premixed nature also to that combustion. We have discussed some aspects of this when we were discussing stability diagram of premixed flames, stability diagrams of burners. Remember all these lines, okay? And then we identified a yellow tip zone, a lift off zone, a flashback zone, and between amongst these three lines there was a safe zone where you could actually design your burner. So in that context we also discussed that there is some air mixed with the fuel which we call the primary air, but there is also a secondary air. Okay. So it can be somewhat premixed with air, but then the combustion is completed outside with the help of secondary air, so that is more non-premixed. Okay. Now, what is important about non-premixed combustion? Why do we want to study this? So if you want to study a flame like this, where you are sending a fuel stream, just fuel mind you, only fuel through the tube, not mixed with air. Suppose we want to study this problem. This is oxidizer outside. Then what are we interested in? Let us say we call this an x coordinate from here, and this is like r coordinate. Then one of the things that we are interested in, of course, is that we will try to find t as a function of both x and r. Okay, so how temperature changes all over the domain, that may be something of interest, because maybe you are using this flame to heat something. So you need to know where the temperature is maximum, how the temperature falls off from the flame zone to other parts. Okay. So, if you move away from the flame zone, what temperatures you get? If you move inside towards the center line, what sort of temperatures that you get? These are relevant questions to ask. Then you may ask similar questions about the fuel mass fraction as a function of x and r, and then maybe O2 mass fraction as a function of x and r. And if there are some products, then you can ask similar questions about the product mass fractions also. You can also ask questions about velocities. Like there is a axial velocity, there is a radial velocity, how these things vary in space. Okay, that this is for a steady problem. This is for a steady situation, steady flow situation. If this was not steady, then that would mean that you are trying to see how a diffusion flame over a short period of time gets developed. Then that's a transient problem. Then everything is also a function of time apart from x and r. So these are important questions to learn about diffusion flame. Now apart from that, we are often interested in this thing. This is flame length. This is length of the flame. So length of the flame, that is the size of the flame and the shape of the flame, these are also often of interest to us. Why? Suppose we are trying to heat something, and suppose we want to heat this surface here with the flame, then you need to know what is the height of the flame, obviously, because if the height is too small, if it is just a small flame here, then it may not be able to heat this surface, and if it is too large, there is too much of flame impingement. Cold fuel will go and strike the surface and stuff like that, so that you don't want. And flame length is of course important in a lot of these heating applications for which small laminar flames can be used. As always, as we have seen for premix flames, laminar flames are not the complete story. In fact, they are not even the most important part of the story. So turbulent non-premix flames will also come later, and turbulent non-premix flames quite often are more important than turbulent premix than laminar non-premix flames. But still, again, for the same reasons that we had for premix flames, we have to first understand laminar non-premix flames and then try to understand whatever we can of turbulent non-premix flames. And starting with laminar non-premix flames, let's see something about flame shapes. Suppose you have an annular kind of arrangement, and you are sending fuel through this, and outside you have oxidizer in this outer tube. Then you can actually get to see a flame shape which is like this, or a flame shape which is more like this, the red one. Okay. Both the shapes are possible. So the first one, this one in black, it's a closed shape, and the one in red, actually it's opening up, the flame is kind of opening up and getting terminated at the wall of the outer tube, right. If you think about it, it's possible. You may not have seen this, but it's possible. And if I ask you, just by looking at it, when do you think we are going to get 1 and when do you think we are going to get 2? There is, mind you, a fuel flow rate here, and there is some oxidizer flow rate in the annulus, that is in the space between the inner tube and the outer tube. Okay. So when do you think we are going to get 1 and when do we think we are going to get 2?
If the fuel rate is small, then it will try to move towards oxygen to get combustion. And if the fuel speed is high, then oxygen will try to move towards this. So if fuel speed is small, it will be on the outer side, and if fuel speed is higher than this way.
Okay. So what has happened is you are just trying to answer based on what you think seems to be reasonable, right, from your instinct. So what happens is, if you increase the if the oxidizer for a given fuel flow rate, let's think about a given fuel flow rate. For a given fuel flow rate, if you have small oxidizer flow rate, then you will like to get state 2, the 2 kind of flame. Okay. and if you increase the oxidizer flow rate, then this sort of shape will try to close on the center line. So, this is like a flame which is opening like a flower, and it will close, it will look more like a bud and give you shape 1. So, we can say that 1 is an over ventilated flame, and 2 is an under ventilated flame. Okay, so, this is very much possible. The other shape that I had drawn few minutes back, just at the beginning of the lecture, this did not have an outer tube, this did not have an outer flow, but this was an quiescent infinite oxidizer field, right. That is this one. So, these problems can be studied to understand more about non-premix flames. Now, before if you say in case of LPG it will be an over ventilated flame, then that does not completely define the problem. No, it has to be, see what I am trying to say here is that for a given fuel flow rate, if the oxidizer flow rate is sufficiently high, then you are going to get this over ventilated flame, and if it is low, then you are going to get this. But then again, just think about it, I am just saying high or low. Okay. I am saying if oxidizer flow rate is adequate, then adequately high, then you are going to get this over ventilated flame. But adequate compared to what? That we have not discussed so far. Okay, that we have to slowly understand. Okay. Now, in this context, of course, the same question will come once more. What is the flame? Flame is that zone where maximum reaction is taking place, correct? But how do we define a flame for a non-premixed situation? So, for a premixed flame, this is where the unburnt gas was getting converted to burnt gas, and then there was an unburnt side, there was a burnt side, things like that. Here, what is the flame? Fuel coming from here, oxidizer coming from here. They meet in this zone, and this is the zone where fuel and oxidizer both get consumed adequately, and the flame is that zone where the reaction rate is high, fuel and oxidizer are getting consumed adequately, coming to the lowest values, and then giving you this surface. It so happens that this is also the zone which corresponds to stoichiometric conditions. Okay. If you take a mass flux of fuel going to this flame, and if you take a mass flux of oxidizer going towards the flame, if you take a ratio of that, that will be in stoichiometric proportions if the surface that you have chosen is the flame. Okay. So, I will come back to this in more detail. This is just an introduction. Today, we are just looking at some aspects of laminar premix flames. These will evolve, these discussions will evolve as we go on. Okay. So, what we want to do is, as I said, we want to do essentially a laminar jet flame. So, just this one and no outer tube also, but in infinite oxidizer field. This is what we finally want to do. But before that, it is actually helpful if you look at a situation where we do not have a flame. We do not have a flame, just have a fuel coming out of this. So, a fuel jet, a non-reacting fuel jet in an outside atmosphere of oxidizer. So, what do you expect will happen? You will have this sort of a jet developing. Okay. Now, you may have studied something about jets and fluid mechanics, but this is a situation where you have two different substances. So, one is oxidizer, other is a fuel, and fuel is expanding into, coming out of a nozzle and expanding into an infinite oxidizer field. Okay. If you look at Turns's book, he has given some analysis, some equations of that, but we are not going to do this in detail. We are just going to look at some broad features of this. Essential features of a non-reacting laminar jet. So, this is a non-reacting jet. Okay. So, the first discussion is about non-reacting jet, and stuff that I tell you in the next few minutes is about non-reacting jet. And let us take a look at this one. I think all right. So, this is for a non-reacting laminar fuel jet issuing into an infinite reservoir of quiescent air. So, the air is not moving and it is an infinite reservoir, it is not limited, just fuel coming out. And we assume that for simplicity, the velocity profile is uniform at the tube exit. So, this is a tube, the tube of diameter 2r. X gets measured from the burner exit plane. So, x goes up like this and this is x equal to 0. X1 and x2 that are shown, these are just some planes. These are planes which are parallel to the burner exit plane. So, x equal to x1, x equal to x2. This and this, they show the jet edge. Okay. Of course, it is axisymmetric. So, it is not like it has got two jet edges, it is one continuous jet edge. Now, this much probably you know that okay, if you send a stream like this, it will expand and it will give you a jet, right, that you know from fluid mechanics. You probably also know that the jet is actually widening because it is also entraining air, surrounding air, correct. The jet also has a potential core. Now, what is a potential core? So, what is marked here is a potential core. Now, the potential core is unaffected by the mixing process. Of course, there is mixing taking place, right, because the fuel is expanding and it is also entraining air. So, you have fuel with air, but this potential core is unaffected by mixing. In this zone, the effects of viscous shear and diffusion have not yet been felt. So, there is viscous shear and there is diffusion, mass diffusion. These things have not been felt in the potential core. So, whatever you are sending through the nozzle you are sending some velocity. We are saying it is a uniform velocity. That velocity actually is maintained within the potential core. As long as we are within the potential core, you have the same velocity. And the nozzle fluid mass fraction is also the same inside the potential core. Okay. So, if you are sending only fuel, let us say if you are sending only propane, then the propane mass fraction in the jet which is coming out of the nozzle is 1. So, that same 1 is maintained within the potential core. Okay. Now, we are going to look at some of these plots here. Actually, we can look at these primarily. So, it shows two quantities, Vx by Ve and Yf. Now, what is Ve? Ve is the velocity at the exit of the tube. Okay, Ve is that uniform velocity at the exit of the tube, and Vx is the axial component of velocity. So, anywhere in the domain there is a axial component and there is a radial component, correct. We are assuming an axisymmetric situation. So, the third component we are not writing, but there will be a Vx, there will be Vr. So, if you take the axial velocity, divide that by the velocity that you are sending the fuel with, that is Ve, then Vx by Ve can be plotted. Now, Vx by Ve is uniformly 1 over the radial distance 0 to r at the exit of the nozzle. At the exit of the nozzle, see this plot which you see, that corresponds to x equal to 0. This is x equal to 0, nozzle exit plane. So, this corresponds to x equal to 0. So, in this region the quantity Vx by Ve is actually equal to 1, all right, because this is what you are sending, no surprises, it is a uniform velocity profile, that is what it shows. But it also shows another thing, this same line, same set of two lines actually also shows Yf. Yf is also 1 at the exit of the tube. So, it is 1 between the center line is here 0, between the center line and at capital R is the radius of the tube, it is just equal to 1. All right. Now, what happens if you move to another height? So, from here you go to the height x1. Okay. So, you look at this plane, and at this plane you will see that Vx by Ve and Yf both have this sort of a variation. So, let us look at what all have changed. What are your observations on this? First of all, it is no longer that square kind of profile, it is actually this sort of a profile is called a top hat profile. Okay. So, it is like a hat, no, part of a hat. That is what it looks like, but it is now rounded. So, that is one difference. What are the other differences that you see? Anybody would like to respond on this one? Yes. So, Vx by Ve at the center line has decreased. You know, it was 1 here, now it is a value less than 1, correct? It is a value less than 1. So, that is one observation. So, the center line velocity is decaying, okay. And somewhere else velocity has actually increased, isn't it? Where? In some radial position outside let us say outside capital R, that is outside this, you now have some velocity. Why has that happened? Yeah. So, because of momentum diffusion actually the jet is expanding, the jet has become wider. Okay. So, now your velocity is here. So, jet has become wider, that is what it shows. And same logic for this plot also, this curve also. Again Vx by Ve and Yf have similar profiles, that is why they are both shown with the same curve. Yf will do the same thing, that is Yf center line value will be less than 1, and as you go up along the axial direction it will keep decreasing. So, the value here is less than 1 and the value here is less than the value which you got in this case, correct. And now there is more velocity in this region and the extent of the jet of course is increasing, that you can see from here. Okay. So, that is the situation. This also you will be able to interpret, this is Vxo divided by Ve. What is that? Center line velocity. Okay. So, this is center line velocity. Center line velocity is actually 1 up to the potential core, but then after that it keeps on decreasing as you go up. Okay. Similar thing for Yf.
What did you mention on the potential core?
Potential core is that region where the essentially the nozzle quantities, there is the velocity profile as the velocity magnitude as well as the fuel mass fraction, these are not affected. So, there is a narrow zone within which these are not affected. So, then the potential zone in the potential core, the effect of viscous shear and diffusion are not felt significantly. Okay. So, after that the decay really starts happening. So, this is about these are some features about non-reacting jet. So, what we understand from all this is that as one goes downstream more and more, the fuel diffuses into the oxidizer and at infinity there is no fuel left. Okay. At infinity there will not be any fuel left. You saw the fuel mass fraction profile. As you move out radially, it starts building up as you move away from the top of the burner, but it actually has to come to 0. And also the other point is that throughout the entire flow field, the initial jet momentum meaning the momentum with which the jet is coming out of the nozzle, that has to be conserved. So the jet issues into the surrounding air and some of its momentum is transferred into the air, thus the velocity of the jet decreases. The jet is coming with some momentum, transferring some momentum to air, so the jet velocity actually decreases, while greater and greater quantities of air are also entrained into the jet as it proceeds downstream. So there is entrainment also happening. Okay. And there are some quantities which we can also define with respect to these jets. One is there is a jet Reynolds number, which is this E for exit, J for jet, E for exit. So that we can understand the notation. So this is the jet Reynolds number. There are a few other important quantities regarding jets. So we'll use a picture to show you that. So there is something called a jet half width. Jet half width, which is denoted by R half. So what is R half? R half is that location, that radial location where the velocity actually becomes half the center line value. Okay, do we understand this? This is Vx as a function of the radial coordinate divided by Vx0. Right? So Vx0 is the center line value, center line velocity. So any Vx divided by the center line value will actually give you a fractional number except the center line value itself. So at the center line it's 1 and then it decreases. So where this ratio is half, that location is jet half width. Okay, that is the jet half width. And the jet half width is for a particular value of x, correct? If you look at this is at a particular x, right? At a particular x plane, you are moving in the radial direction, and that's how we got this velocity profile. If you go to another x plane, the R half value will change, right? But R half and x, if you show at x the value of R half, another x, another value of R half, like that, then you can define something like this. Then you can define an angle alpha which corresponds to a jet spreading angle. So this jet spreading angle is actually alpha, which is tan inverse R half by x, and R half by x is this. I am just stating without going into details. R half by x is 2.97 divided by Rej. Rej is the jet Reynolds number. R half is that jet half width. So R half here divided by x, that must be tan alpha. Okay, so alpha is tan inverse R half by x, but from somewhere else I am also saying that R half divided by x is equal to 2.97 divided by Reynolds number. So what that tells us is that if we have a jet with higher momentum, then the jet Reynolds number is higher, and then R half by x will be smaller, and then alpha will be smaller, right? So, high Reynolds number jets are actually narrower, correct. So, this is something which we can see from this relation, from all this. And we are not deriving this or looking at this in great detail, but these are features which we will try to appreciate, because before we go to flame we should know the situation of what happens if we have a jet. Now, we are talking about velocities. Now, YF, that is the fuel mass fraction, this also decays inversely with distance and is directly proportional to the jet Reynolds number. Okay. There are few conservation equations, integral form of conservation equations which can be written. I will just write them, and I think you will be able to make out that these are correct. Again, this is for non-reacting laminar jet, okay, into a quiescent infinite reservoir of oxidizer. The integral form momentum conservation gives and we can also have So, I just wrote this, and I trust you will be able to verify this in your mind. So, fuel mass is of course conserved, isn't it? You are sending fuel at a certain rate. Where will the fuel go? Fuel will go somewhere in the domain. So, if we integrate R0 to infinity, it will be able to account for all the fuel which has left the nozzle, correct? That is what the fuel mass conservation means. And the momentum conservation means similarly that the momentum that you are sending out must be getting transferred over the domain. Okay.
What is capital R here, sir?
Capital R is the radius of the nozzle. Radius of the nozzle. So, we actually wrote some time back, we had this figure, right? Yeah. All right. So, this is about the non-reacting jet. So, what did we learn from this? We learned that okay, there is a centerline decay of velocity, fuel mass fraction, there is an expansion of the jet, the fuel is mass of the fuel is conserved, and the momentum that you are sending through the tube is also conserved. Other thing that we learned is that of course, the fuel is fuel jet actually, because of its interaction with the surrounding air, surrounding oxidizer, is able to entrain air also in the process. Right? So, these are some broad features that we should know. Now, we will have to go to finally jet flame. And when we are talking about jet flame, we are talking about laminar situation, of course. And so, what is a flame? The flame surface is the locus of the points where the equivalence ratio equals unity. So, this is Now, this is a little bit tricky. Okay. It is tricky because let us think about what happens in a flame. What we understood today is that there is some flame, and we expect that the fuel come this way, and the O2 will come this way, O2 of the oxidizer. They will react at the flame, isn't it? We expect both of them to get consumed. So, if they are getting consumed, what is the idea of equivalence ratio? That is one question that will come to your mind, because there is no, ultimately there is almost no fuel, almost no oxidizer there. So, what is equivalence ratio? That is one question. The other question is that we have been familiar with equivalence ratio, but then we have been thinking also in terms of the fuel oxidizer mixture, correct? But do we have a mixture here? Not exactly. Yeah, so ultimately you have fuel going into the flame and oxidizer going into the flame. What I was telling you a few minutes back is that the mass fluxes of these going into the flame surface, and you see these two arrows of fuel and O2, the mass fluxes will be in such ratio that the mass they represent a stoichiometric surface. So, the mass fluxes, the ratio of the fluxes will go towards stoichiometric. That is what it means, that equivalence ratio will be equal to 1. The other way of looking at it is that the products will get formed at the flame, because the fuel and the oxidizer are meeting at the flame. The formation of the products, the product composition that we will get will correspond to a stoichiometric situation. So, that is why we say that the flame is the locus of points where the equivalence ratio equals unity. And apart from that, we also want to say what is the flame length. So, this is flame length. How do we define the flame length? We can say that one way of writing this is phi at r equal to 0, x equal to LF is equal to 1. Is that correct? Phi is the equivalence ratio. So, that is 1 when you are on the axis, meaning r equal to 0, and in the axial direction, that is in x, you have moved the distance LF. So, you have reached here. So, then you get phi equal to 1. Okay. So, flame length is that value of x on the axis of the flame where you reach equivalence ratio of 1. Now, we will do jet flame in more detail a little later, but in Turns's book, Laminar diffusion flame is in Turns 3rd edition book, it is in chapter 9. Okay. And by using arguments regarding the non-reacting jet, he actually presents the following relation for LF. So, LF is so he got this expression. Okay. Now, let me just first tell you what these are. How he got this, so that we will see later. So, this we will see later, but let me explain the notations. QF is the volumetric flow rate of fuel through the tube. So, we know that this is fuel coming out. QF is the volumetric flow rate of fuel through the tube. D is the diffusion coefficient, and YF stoichiometric is actually that stoichiometric value of mass fraction of fuel, which is mf divided by ma plus mf, which is correct. So, this is a stoichiometric situation. So, if YF is of course mf divided by ma plus mf, because you have only air and fuel, and if you divide the numerator and the denominator by mf, then you get this. So, that is what YF stoichiometric is. Now, this relation, even though I have not told you exactly how he got it, and will not be able to do that today, because today we may run out of time, but he got this relation using the derivation that he has for a non-reacting jet. Okay. So far we have not done a reacting jet. So, non-reacting jet also, whatever is given in Terns's book, all the derivations, everything we have not done, but I am just picking up this he has got from the non-reacting jet analysis. And according to what he is giving, this is something interesting. It tells you that the length of the flame will depend on the volume flow rate of the fuel, not on the velocity of the fuel separately. Okay. So, this means that other conditions remaining the same, if you have two burners of different diameters which produce the same QF, they will give you the same flame height, the same flame length. That is what this relation tells us. Later on we will see whether experimentally this can be verified or not. So, what I was saying is the flame length is proportional to the volume flow rate of fuel. It is not individually to velocity and area. Okay. So, that is one aspect. The other aspect is that we see that flame length is proportional to 1 over YF stoichiometric. So, it is inversely proportional to YF stoichiometric. Okay. So, what does this mean? If you have a fuel which requires less air for complete combustion, then what can we say about its flame length? Just looking at this expression, just looking at what we have. Less air requirement will give you, so it will give you, if you look at this, then A by F stoichiometric is less if the fuel requires less amount of air. So, YF, which implies YF stoichiometric is what in that case? More, right? More, because its YF stoichiometric is 1 over A by F stoichiometric plus 1, which implies LF is less. So, we can connect these two. We can connect that, okay, there you have a fuel which requires less amount of air for stoichiometric combustion. So, this is valid. This means this. Okay. This means this. So, even though we do not still know how this has come, does this seem reasonable? Again, no, we have not done theory today. Broadly, does it seem reasonable? This is an important result actually. Does it seem reasonable? That if it requires less amount of air, then the flame can be shorter. Okay. So, this makes sense. And you can check this out. How to calculate this? We have, if you have a hydrocarbon,
then fuel needs to travel less distance to
get consumed. Yes. So, that is how we can interpret. So, it requires less surface basically. The fuel, packets of fuel coming out of the nozzle need to travel less distance before they can get consumed, because they need less amount of air. Okay, so if you have let us say hydrocarbon CXHY, then can we write the following for A by F stoichiometric? It is x plus y by 4.76 into W A divided by W F, correct? W for molecular weight. So if you have, let us say, methane, then you know how to calculate this one. If you have propane or butane or something else, you know how to calculate this. So if you take methane and propane, which one will take less amount of air? Suppose we compare methane and propane. Which one is going to take less amount of air?
Propane x plus y by 4 is higher. But
methane will take
MF is again higher. I mean WF.
WF.
I think still the ratio will be.
So you can check this out. You can say choose methane, ethane, propane, butane, like that, and use this expression to calculate air fuel ratio stoichiometric and see which one requires less air. And depending on which one requires less air, you can think about which fuel is going to give flames of shorter length. Flame length is important because I told you in burner design, you need to know what sort of flame length you are going to get. Okay. So what we are running out of time today. What we will do next class is that on Wednesday, we will try to understand this little better. This I have just picked up from somewhere. So we need to understand this better, and then we will also do some theory of, and the theory will take some time. We will do some theory of how to get the various profiles. So what I told you today is that when we have this flame, we are interested in knowing how temperature varies spatially at various points, how velocity x component varies at various points, how VR varies at various points, how fuel mass fraction, oxidizer mass fractions, these things change with the spatial coordinate. So we need to know that, and to do that we cannot stop just at the flame length. So we have to take conservation equations and try to solve them. So this is going to take quite a few lectures, and we'll start that job slowly from the next class. Okay, so we'll stop here. Thank you.